Okay, so here's the continuation of the video on exponential and logarithmic functions. Before I go on to the next part, though, I realise I missed something out, namely inequalities. Let's just get this right. Yeah, so inequalities. I remember actually this doesn't really come up so much on the additional maths exam, but it certainly comes up on the P2 exam, which is instead of solving equations like the ones we solved, sometimes we also have to solve inequalities, and it's actually quite simple because the main thing is, yet again I come back to this point, remember that this function here, this is 2 to the x, and also this function here, which I didn't actually write down, but is log base 2x. So either a to the power x, where a is positive, or log base ax. They're both increasing functions, monotonic increasing, and it means that not only a equals b and fa equals fb are equivalent statements, but also the inequality. For example, if a is less than b, it follows that 2 to the a is less than 2 to the b. And if a is bigger than b, it follows that 2 to the a is bigger than 2 to the b. So, you know, because obviously this is an increasing function, okay? So you can use that in inequalities, but I don't think I'll say any more about it right now because it's not really that relevant to additional maths. On the other hand, let's stay where we were. On the other hand, the remaining section that we've got to think about is the linear law problems here. So I guess the best way to start looking at this is to look at the syllabus, and I think here we are. On the syllabus you see that it says a student should be able to transform given relationships, including y equals ax to the n and y equals ab to the power x, to a straight line form, and hence determine unknown constants by calculating gradient or intercept of the transformed graph. So what does this mean? People sometimes find it very mysterious. Let's think about these graphs first of all. I'll start by drawing another big set of axes here. So let's do a nice big y-axis, and a nice big x-axis. Whoops. Maybe somewhere like, now let me think about this, probably like that. Okay, so I'm looking now at two kinds of graphs. The first graph is ax to the n, so obviously this is usually going to be a curve, right? And the other kind of graph is a times b to the x. Now let's be careful here. A times b to the x or rather its value when x is 0 is a and not 1, and b here could be a number like 2 or 3 or e or anything else. And as before, we're going to get this kind of exponential shaped graph like that, okay? So this could be y equals a b to the x. And what this is all talking about is cases where you have scientific data. Here's one simple example. The force on a particle, suppose a particle is falling through the air, falling down to the ground. There's some gravitational acceleration, but there might also be a force F, which is air resistance, pulling it back. Now when we do experiments with air resistance, we find it doesn't follow a very simple mathematical law, but it can sometimes be modelled. I want to emphasize this word, modelled, as taking a form like this. F equals k v to the power n, where v is the velocity and n might be 1 or 2, or could be like 1.7 or 2.4. Question mark. Yeah, we don't actually know. Maybe our scientific knowledge is not enough to really be sure. Meanwhile, k might be just any number at all, okay? After all, the force is measured in newtons, and so we have to multiply the velocity or the power of the velocity by some constant to get the force. This is a very common situation in science, and the problem you have is that you can measure the force, you can measure the air resistance force for different values of V, but you maybe don't know exactly what these numbers n and k are in a scientific experiment. You're trying to find out what they are. Now suppose the logical thing to do, let's just write that formula again as a fundamental idea. F equals kv to the n. K and n are unknown. Yeah. To try and find the values of k and n, you could do something like this. Have a column for velocity and a column for force, and you could measure different values. v1, f1, v2, f2. Okay, so this data could come from experiments. And what you want to do is to use this data, so use all of this data as a set to help you figure out the correct values of these quantities. Now the problem that arises if you make a graph, if you directly make a graph of this data, then the shape of your graph is going to be exactly like this curve here. It's going to be a curve, and it's going to be very difficult just from looking at the curve, or rather looking at the data, to deduce the exact form of the curve, because the data will not be exact. So the values that you plot on the graph might look like this. There will be some noise, there will be some inaccuracy in your calculations, and it's very difficult for the human eye to judge the correct curve just from looking at the data points. So what I've shown in red crosses here, you can't really deduce what this black curve should be. So what we do to overcome this problem, and it's only, there's a lot more to this story than what I'm saying, but I'm giving you the basics, the most elementary way to understand it. So what we can try to do is use the fact that if we take the logarithm of the equation, we, instead of a curve, get a straight line. Now what do I mean by that? Well, I'm going to go back to basics. I'm going to go back to the form x as the independent variable and y as the dependent variable. So instead of f equals kv to the n, I'm going to write, well, as we've just seen, I'm going to write y equals a times b to the power x. Sorry, let me get this right. Okay, we don't have to worry about the details. Let's just say it's the same basic kind of equation. No, I'm sorry, I know what I did wrong. Yeah, sorry, the kv to the n type is similar to the ax to the n type. So actually I drew the wrong arrow there. The arrow should have been pointing towards this one here. Okay, so as I was just saying with the science experiment, we're going to have values of x and y, x1, y1, x2, y2, and we're going to try to deduce the shape of the graph. The trick is we just simply take the logarithms of both sides of the equation. So if you remember nothing else about this section, remember that the idea is to take logarithms of both sides of the equation and change to a straight line graph. Instead of a curve, we get a straight line. That's the key to it. Now let's see how that works. Let's apply the laws of logarithms. We see on the left hand side lny, so ln meaning natural logarithm. On the right hand side we use the first law of logarithms to split into two parts. But now we can also use the second law of logarithms, the power law, to take the n outside as a multiple, plus n logarithm x. Now, when you look at this equation, you might not realize that it's a straight line at first, but it is a straight line if we define different variables. Just assume that capital Y is what we mean by log Y, and assume that capital X is what we mean by ln or log x. Then it follows that we have the straight line equation y is equal to ln A plus n capital X. So what kind of graph is that? Well, that's just a simple straight line graph, and I'm just going to draw it roughly here. Excuse me for the roughness. Something like that. Okay, so here, what is the y-axis intercept? If this is capital Y now, not lowercase y, it's capital Y, so it's really the logarithm of the first y, and this is capital X, which is the logarithm of the first x. Then the question becomes, what is the y-axis intercept and the gradient of this line? Now I'm just going to draw it a little bit more neatly so we can work with it properly. So you have a think about that question. What's the gradient? And so looking up here, yeah, and up here, what's the gradient and what's the intercept? So now I'm going to draw the graph a bit more carefully. What do I need to do here? I need to draw a line here. And one further line. Let's draw one more line. Okay. Maybe that will work, yeah. Oops, that didn't work, did it? Interesting. I'm not quite sure how to deal with that. Maybe I'll just leave it like that. That's good enough. So it's supposed to be a straight line graph. So here we have capital Y, here we have capital X, in brackets that's ln of little x, in brackets that's ln of little y, and this is the line. What is the y-axis intercept? The answer is the y-axis intercept is the value of the constant ln A. Now what is the gradient of the line? Gradient would be, of course, n. Yeah? So the two numbers that we want can be found. Numbers A and n can be found from graph. We can find A because we can find ln A, and then to find A, well, that's just simply e to the power of ln A by definition, because ln and e to the x are inverse functions, and n can be found as a change in capital Y over the change in capital X, using the method that you should be well familiar with, how to find the gradient. Now remember, we don't actually have this exact line. What we have is some data. Let's draw some examples of what we mean. We have some data such as this. We have x values, we have y values. You know, like 1.1, 3.2, 1.8, 7.4, 2.5, 12.6, and so on. These are just made up examples, they're not real data, so please don't try to calculate it. And so what you're doing is you're making two more columns, capital X, where this is ln of 1.1, this is ln of 1.8, and so on. Capital Y, which is the logarithm of little y, ln 3.2, ln 7.4, and so on. And then you're making your graph here from these two columns here. These two columns are used to make the graph, and that will give you a set of points on the graph, such as like this, and this, and this, and this. And then you make a line of best fit, yeah? So the line that you're drawing with your ruler on the graph is the line of best fit, as you do in science, in physics and chemistry and so on. Having made that line, you can then estimate. You can then estimate the intercept and estimate the gradient. Having estimated the intercept and the gradient, that data can be used to feed in to these two calculations, which will give you your estimates for A and N. And that usually is what you need to do to solve the question. Now, what I've just shown you is one of the two types. There is another type, a times b to the power x. So let's consider that second case, but actually the method is almost identical. So in that second case we have y equals a times b to the power x. Here b will be a positive number. As we already discussed, this kind of thing should not be negative, and almost always a will be a positive number, but I'll put that in brackets because I don't think it actually has to be. It just is usually. Alright, so as before, the task is to use data, estimate A and B from graph. So to make the graph, we want to make a straight line graph. So we need to take logarithms, yeah? Again, as before, let's do the same thing. ln y equals ln a b to the power x. Now before I go any further, you might want to pause the video and try to see if you can figure out what will be the value of the intercept of the straight line graph and what will be the value of the gradient. Okay, now I'm going to go through the process. So ln y is equal to ln a, capital A this time, plus ln b to the power x. As before, we will take the x outside using the power law. Ln y equals ln a plus x ln b. And you'll see that although it looks very similar, there are some slight differences here. We define capital Y equals ln y, but now capital X should just be x, not ln x, because look carefully at this equation, yeah? So now if I repeat the graph before, I don't think I need to draw it again. It's the same basic idea, isn't it? Let me just make a copy of it. Hopefully I can get this right. Yeah, that's good enough. So I'll make a copy of this graph, but I'm going to make some slight changes. Maybe I can put it here. Yeah, I think I can put it here. Okay, good. What's the changes? Well, first of all, the x variable is no longer ln x, it's just x. Sorry, there it is. So that's an important difference in this case. The y variable is still ln y. But now what about the gradient and the intercept? Well, you can see that the straight line equation looks something like this. There we go. Capital Y, ln y is capital Y, is equal to ln capital A plus ln B times x. So the intercept is still the logarithm of A, well this time capital A, but the gradient is now ln B. So if you remember, our task was to estimate A and B from the graph, and we can see now how we do that. We use the same method as before. We calculate, in fact capital X will just be X. Let me make a copy of this so we can do the same process. Whoops, didn't quite get that right. There we go. maybe I can fit this down here. There we go. So now the table will be almost the same, except one thing. The values of x will just be the same, will be unchanged. So you almost don't really need to make another column here. 1.1, 1.8, and so on. The values of y, you will take the logarithm. You will plot these two data sets onto this graph, if that works there. Plot those two data that data onto that graph, calculate the gradient and get lnb, calculate the intercept and get lna. So I hope that's all fairly clear. That's the basic method. You'll often be doing this on graph paper and try to draw the graphs as accurately as possible. Now let's go back and look at an exam question of this type. Sorry, I've lost it. Where's it gone? Not there, for sure. Where has the exam question gone? It's here. There we go. Right, so let's have a quick look at this exam question. The first point you notice is that you've actually got data here. So they're giving you data, x and y values, and you can see here it's the second type of equation that we're dealing with. There's only those two types, no others. Well, I'm not sure if I can say that, but usually it's one of those two on the exam. If it's something slightly different, then use the same principle. Take logarithms of both sides and convert it to a straight line. So here they ask you to use the data to draw the straight line graph, and they actually tell you to use log base 10. If they don't tell you what base to use, it doesn't matter. That's important to understand. It will work anyway, whichever base you use. So in this example you would use log base 10. In other examples you can use log base e. It's usually the easiest because you have that on the calculator. They give you the scale, and then they ask you to plot the graph, and then they ask you to estimate a and b. Okay, so we just learned how to do that. They then say on the same diagram, draw the straight line representing y equals 2 to the x, and hence find the value of x for which ab to the x equals 2 to the x. Now obviously I'm not actually going to calculate everything here, but do we see the basic idea? If we were looking at this graph and we were told to find the value of x for which 2 to the x equals ab to the x, well, we will be drawing another straight line, y equals 2 to the x. To find the straight line here, we would need to take the logarithm of both sides. Log y equals x log 2, natural log 2. Sorry, I should be a little clearer. In this exam question they asked for LG, so let's do LG. LG y equals x LG2. So what kind of straight line is this? It's y equals LG2 x. So it has gradient LG2 and it has intercept 0. So it's going to be very simple straight line graph through the origin with gradient LG2. So you'd have that graph, and then you'd have your other graph which you've already drawn, and there would be a single point there where the two graphs meet, and you could estimate that by just looking and finding that point. So I hope it's clear how you can do questions like that. There are sometimes more difficult examples, but in every case the basic principle is to take your starting equation and take the logarithm of both sides. That should always get you to the answer. Okay, so now we've covered the linear law idea. You certainly should try the examples in the book, have a good practice there, and I've also showed you now 3 exam questions, so hopefully that will be enough on that topic, and I'll leave it there for now. Thank you very much.